some things also happen, isn't it? There are some places mosquitoes in terms of abundance are more compared to the other, right? For instance, people who are living around the riverine area may have more of abundance of mosquito than people, or people who practice poor, drainage systems and co. So there are environmental factors, there are climatic factors, that play within the dynamics of the malaria itself, the mosquito, the human interaction, mosquito-human interaction, and all of that to really now give birth to malaria. And in mathematical modeling, which the focus of mathematical modeling in this case now has to be, mechanistic approach. Is that okay? Where all the factors that work together to determine the state of the system, of that system, they are all factored into the system model. Are we together? We are interested in looking at all the factors that work together to determine the state of that system. Such situation, we are talking about mechanistic models. And a very, very notable one for that is what we call deterministic compartmental models, which we see also in the course of this lecture. Is that okay? And there are many other ones that are mechanistic in nature. We have the stochastic one as well. And we have agent-based models as well that are mechanistic in nature. So now the focus of this one will be on mechanistic models. And we want to see what are the basic things that we need, as we call the title, Mathematical Foundation for Infectious Disease Modeling. Like Prof mentioned the other time, there are a lot of mathematical equations and expressions that we have learned that are very, very useful in, the processes of coming up with a reliable model, building a reliable model, building a very good model that you can also calibrate with data. And so that's what we'll be looking at. So like I said, mathematical concepts can be used to explain biological processes or dynamics. So in this case, you see the word processes. So mechanistic model that we are looking at also, they are called process-based model. Is that okay? Process-based models. So there are processes that are involved when it talks about a system running. So we are looking at, so the fact that there are mathematical terms that we need to bring in, right? And there are biological terms. Now we just mentioned in the case of malaria now. For malaria is not first and foremost mathematics, we know, right? But ability to bring a certain aspect of that disease and represent it by the needed mathematics, is also cause for us to look into this issue of foundation, the foundation, the mathematical foundation. Because for us to represent the process well, we must understand the process, we must understand the biology, and then know the kind of maths that can respond or that can represent that process. Are we together? So we must know what the process is, and we must be able to fetch out the kind of maths that can represent that kind of process. All right? For instance, now I'm going to start gently with us with let's look at this now, this equation of straight line, right? We are all familiar with it. How many of us, of course, this is even at secondary school level, you did equation of straight line. So even if you have forgotten, I think this would be a good one to remind us. Equation of straight line, right? Y equals to either use S or you use T as in this case now. Plus what? Our M is what? Is gradient, right? And the C is what? It's the intercept, isn't it? You see, as this is just a maths equation concept lying somewhere. But you see, some persons look at an infectious disease and consider that in the course, like we talked about mosquito biting human being, right? That there is something called mosquito biting rate, isn't it? Are we together? It's called what? Mosquito biting rate. So this is a linear function. And we do know that in most of the models, mathematical models that we have, we just represent this as a single, as a constant value, biting rate, mosquito biting rate. But in reality, it's not constant, right? It changes over time, isn't it? Are we together? Okay, not only that, some other things can also affect it. Yeah? Some other things can also affect it. The bed, like bed net usage. If you are using bed net, it can affect the way mosquito biting rates comes out. Are we together? So somebody is looking at how does bed net alter the mosquito biting rates, and then model this as a linear function, as beta of B equals to beta max minus beta min into B naught. What are we saying? Now, beta max representing the maximum biting rate. Is that okay? And then beta min representing the minimum mosquito biting rate. It's possible you have collected data over time and you see that, okay, in the course of the years, you realize that the minimum biting rate is this, the maximum biting rate is when there is no bed net, right? But as bed net comes in, bed net moderates what happens. Is that okay? Bed net moderates it. And so it moderates it with this kind of relationship where B naught is taken as the bed net usage. Is that okay? The proportion of bed net usage. And if you look at that equation very well, you realize that once B naught, because both B max and B min, they are both constant. Are we together? The only thing that changes there is the what? Is the bed net usage. So if we increase B naught, what happens? What happens? Yeah? Now, I want you to see something. B max minus B min is positive. Do you know it's positive? Because B max is bigger than B min. So when you subtract that, it gives you a positive value, isn't it? Okay, so B naught also now is positive. And when you take all that expression together, they are all positive, isn't it? So you are subtracting actually positive value from B max. And the value you are subtracting is smaller than B max, isn't it? Because if you look at B max minus B min, it will be smaller than B max. Are we together? So now you are subtracting a smaller value. So this is not going to be negative in any way. Are we together? So now as B naught increases, what happens? That value, no, we cannot have negative value. B naught is between 0 and 1, right? Because we are talking about proportion. We are talking about proportion. As B naught increases, what happens to that biting rate? It reduces. Yeah? As B naught increases, what happens to biting rate? It reduces. So that means it's capturing a linear relationship between biting rate and what? Bed net usage. Saying as biting rate, as a net usage increases, biting rate does what? Reduces. So that kind of understanding, that kind of, we know that it's acceptable, right? That bed net will reduce biting rates. And so somebody came up and said, okay, let's use a linear equation to represent that kind of relationship. And we have this. And this in place of biting rates, rather than use biting rate that is not dependent on bed net usage, we can now use this. So I'm just saying, for instance, that we just need to be aware. Please, this thing is not moving. So you see the plot of that graph, right? You can see it's a decreasing function, right? You are seeing mosquito biting rate as a decreasing function of bed net usage. So obviously, some assumptions have gone into this, right? Some assumptions have gone into this. And that's why for mechanistic models, assumptions are very, very important. Now, your assumption is also a kind of limitation to your model, because your assumption tells us, because now you have assumed that biting rate is linearly relates with the relationship between biting rate and bed net usage is what? It's linear, right? It's inversely proportional. But you also know that there are some other things that may not make that to be true. Is that okay? So every model is limited by its assumption. And you need to be clear about it when writing. You have made this assumption in the course of developing the model, which we talk about the model development later. Or we're just looking at how can we bring in functions or equations, simple equations, things that we know mathematically before now, into this. Is not moving again. Okay. Now, other function that you are familiar with, you also know trigonometric function, right? Are we together? Trigonometric function. These are functions that you can use to capture rise and fall, isn't it? But there are some processes in disease transmission that exhibit such thing, rises and fall, right? Are we together? Where you may need to use such trigonometric function, and we will see very soon as we go on how this kind of function can come into use. And we'll bring it into certain aspects of the model as we later enter into model formulation, different components of the processes that we are capturing, how different functions, simple functions that mathematics functions we can use. Polynomial, we also know what polynomials are, right? These are all functions that can be very, very useful as we go on. Now, I would also want to talk about function of time. Look at this function. We have y equals to f of t. You know that your f of t can be anything, right? It can be sine t as we have it. That means as time changes, the value of the output also does what? Also what? Changes. Like I was mentioning the other time, that unlike the way we represented the bed net usage, mosquito biting rate as a function of bed net usage, and it only varies with bed net usage. We also mentioned the other time that mosquito biting rate is also a function of time, isn't it? Are we together? It's a function of time. Why do we know it's a function of time? How do we know it's a function of time? That can vary with time. Because in terms of season, during rainy season, what should we expect? We have breeding sites all over the place. And then for that, it can bring about more mosquitoes and it can increase biting rate. Is that okay? Are we together? Also, we know that even other things are there. We just mentioned biting rate of mosquito. I'm using malaria as an example now. What about mosquito recruitment? The birth of mosquito itself. Is it not seasonal too? Yeah, it can be seasonal. It's a function of time. Are we together? But sometimes we just use simplifying assumptions and put it as constant. But when you put it as constant, just know that the variability over time, you have been silent about it. So, and you have to come clean about that. So this is a typical example of a function of time. Parameters are key parts of mathematical models, and they give appropriate explanation for transmission dynamics of infectious disease captured with deterministic model. For instance, we'll still talk about this one. We are just bringing it up for us to see. These parameters can either be constant or time dependent. For instance, if you look at this now, in this kind of model, somebody must have come about what we call SIR model before. SIR model, this is an example of a very typical example of SIR model where a population is subdivided into 3 classes: susceptible, infectious, and what? Recovered compartment. It doesn't mean people don't get to heal from malaria, but once you recover from malaria, what happens to you? You go back to being susceptible. So you don't say that you get inside R class and then you got one immunity where you are good, nothing happens to you for a period of time, and then even if mosquito bites you, everything is fine, and then until later when the immunity now wanes and you now go back so that you can be bouncing around, exposing yourself to mosquito bites. No. If you recover today, you use artemisinin and everything gets cleared today, and then you feel that no problem, mosquitoes, you can start coming. When they bite you and you happen to be bitten by an infectious one, what will happen to you again? So it only means that it doesn't, recovery does not do what? Does not confer immunity on you. Is that okay? That's why we are not putting that R there, because if you put R there, you are only saying that recovery also does what? Confers immunity, and either temporal or permanent. If it's permanent, you will not go back to S, right? For some time, you stay there, nothing happens to you while you are in that class. So, but once that immunity wanes, you can then go back. So, but it depends on the disease. So for this disease now, let's assume this is a disease that has a possibility of staying immune for some time. Can you think of such disease that when you recover, it confers immunity on you for some time before the immunity wanes and then you can go back? Can you think of such disease? What do you say? Measles. Okay, you now tell me, is it temporal immunity or permanent? Anyway, permanent, right? Because it's expected to be a childhood disease. Is that okay? So that when you get to our class, you stay there. You are not going back. Anyway, even though we are having some reports now that some adults are also getting it, I don't know how true that is. Okay, but what we are saying in essence is that in this kind of equation, right, our beta and gamma that you are seeing there, they are all constants. Are we together? Beta here is the transmission rate. Hello, are we together? Is the transmission rate, and we take it to be constant. But in reality, do you think transmission rates of diseases are constant in time? Depend, right? Let's look at COVID, for instance. When we say transmission rates, transmission itself is depends on contact, isn't it? Are we together? Transmission of, we are talking about COVID now. You have to, it depends on contact. Are we together? Are we together? Okay, so when somebody, you get access to an infectious person and then something happens, you can get COVID and you are also now beginning to show symptoms. But that transmission rates may change over time depending, right? COVID-19 as of 2019, 2020, is it the same as of today? Is the transmission rate the same today? Things change, right? Over time. But in this situation, we are modeling it as constant. Okay? So we are saying that, let's look at malaria also, coming back to malaria, as I've talked about biting rates. Now we are now looking at some time-dependent parameters. In malaria, we have, we talk about seasonality. Generally, seasonality is a concept in epidemic diseases, because you are talking about systematic, peak of infection, right? At certain time of the year, you are talking about the rise, and that rise and fall that you talk about, that's systematic. Are we together? That at a certain time of the year, you have a peak. At another time of the year, you have a what? You have the trough. What's happening for that? Because we would expect that kind of behavior, I mentioned the other time, like sine function, cosine function. So you don't want to capture that kind of process with a constant function or with a constant parameter. You have to look at it from the perspective of time varying function. And so because we have climatic factors that are responsible for seasonality of malaria. And these factors influence availability of conditions suitable for the sustainability of mosquito population and their activities, for instance. So this seasonal variation can be integrated into a malaria model through the mosquito biting rate as a function of time that leads to the modification of the biting rate. So now we are looking at this kind of function. B of t, which is expressed as B naught, 1 plus BA sine 2 pi P t minus 5. Here, what we are saying in essence is that we are looking at a biting rate that is with respect to time, where the period is P. The period there is P, right? And when we talk about a period, sometimes we can have annual cycles. We can also have, multi-annual cycle. We can have semi-annual cycles, depending on how that, for instance, what drives the seasonality, If it is rainfall that drives the seasonality, in some states, for instance, northern states of Nigeria, you realize that we may likely be talking about annual cycles, isn't it? Because we just simply have the peak once in a year, and then the rain comes, it's very large, and then we go into dry season, then the next year. But there are some states, maybe south, you may be having 2 peaks in a year. You may be like Lagos now, where rainfall is almost all year round. You may not exactly have annual cycle entirely. You can have some semi-annual cycles too, in the sense that the peak may be coming more than once a year. Are we together? Are we together? So depending on what you are capturing, depending on what drives that seasonality. So if, for instance, we are considering P here, which is an annual cycle, then that P becomes 12. Are we together? If you are dealing with monthly data sets, which most of the time we have access to, you are dealing with monthly data set, then it becomes 12 because you are dealing with an annual cycle. Is that okay? And then you see now phi over there is just a phase shift, right? Phase shift. And then B naught there, we are using that to represent the baseline biting rate. Baseline biting rate. That means that in the absence of seasonality, right? If you open that bracket, you just have it as B naught and then other things are there. So that means if the seasonal component were to be absent, so what do we have? That's beta naught, that's B naught. So you can think of a function like this also. And what other disease do you think we have situation of seasonality there too? Can somebody tell me? Cholera, good. Cholera, meaning that we can also capture some component of cholera with what? This kind of seasonal function. What other disease? Lassa fever. What about Lassa fever? Can you tell me what brings about seasonality in Lassa fever? Harvest period, right? The rodents, bats now. Is that okay? And then you know that during rainy season, you have the bushes everywhere. People are planting. The rodents are in the bush, isn't it? And they are multiplying. Because if you get food now, you go multiply, right? They have plenty of food to eat. They grow in size, in number. And then when it is dry season, when people begin to harvest their crops, what happened? So when there is nothing in the bush again to eat now, they begin to follow you home. So they go to your house. It's where the food is available, right? And that is where you have your things unkept and all of that. So you begin to see that during dry season, you may have Lassa fever surge. It's not because they are not there during rainy season, but the rats are in the bush. Is that okay? So those are kind of things you can think about. So meaning that we can begin to look at the transmission dynamics of Lassa fever, also factoring in seasonality. Do we understand? Do we get that now? All right, so let's move on. So this is just a plot of such function, which is a seasonal function. It just goes sinusoidal. Okay, we move on to exponential functions. So exponential functions are very important functions because they help us to model either growth or what? Either growth or what? Decay. Are we together? When you have exponential, say exponential t, of course, this is the mathematical expansion of exponential t, and I will not bore with that. But that t is very important. If t was to, if is positive, if t is positive, you know, we are still looking at function of, we are just, let's take that t to be time, for instance. That means you are looking at a function that grows with time. It grows exponentially with time. As time increases, the function does what? Grows. Sir? No. If it's time, it cannot be negative, of course. Yes, it cannot be negative because you can't be talking about negative time. So this grows with time. Can you give me an example of something that grows over time? Somebody mentioned cholera the other time. What causes cholera? What causes cholera? Bacteria, right? Do I have microbiologists here? Not just cerebral cholera, right? What happens to it? It grows, isn't it? It begins to grow. Bacteria multiplies, even though we know that there's also something we call carrying capacity, which we'll talk about later. But for now, we are looking at the space of growth. As the bacteria begins to grow, you see that you can, at that phase of growth, you can capture it with an exponential function. But we also know that some things decay. Can you give me an example of things that decay? Like when it comes to epidemiology. Decay processes in epidemiology. Adia, can you tell me? Decay processes. Radioactive decay, yes. Okay, epidemiology, we will give example. Have you heard of IRS before? Indoor residual spray? Anything that has to do with chemical intervention. At the beginning, the efficacy can be very high, isn't it? But over time, what happens? It begins to wane. The efficacy begins to wane. So that kind of thing, you can think about a decay function, which is an exponential decay, as a function to use this time around. In that situation, we must not just put t. It has to be minus what? Minus t. So, and depending also on the decay factor, which here we are bringing in k. Yes. Yes, sir. Yes, the same thing also. Thank you, Prof. In population model also, as people die, what happened? What happened to the population? The population decreases. In predator-prey interaction, as the predator preys more on the prey, what happens to? It decreases the population of the prey. Is that okay? So there are some of these things that you see that follows this kind of distribution. Okay, and so we have just plotted, depending on different values of K, right? It tells how fast the decay takes place. With IK, if you have the value of K to be very high, imagine when the value of K is 1. So it decays very fast. So there are situations where we have fast decay and situations where we have what? Slow decay. So the K there can determine how fast the decay takes place. Okay, so we move on. We also have logarithm functions here, which now, so because of our time, I've mentioned situation where we bring in exponential functions. So this is just to exhibit them. For instance, in COVID, we talk about immune response and waning immunity, right? I think we've talked about something like this already. So let's just move on. And then for disease transmission also, sometimes when you have an outbreak, at the beginning of outbreak, what do you notice? What happens? you realize that the cases begin to rise, isn't it? At the beginning of the outbreak, the cases begin to rise. And as the cases are rising, they are rising over time. In that situation, you can also look at that as an exponential growth, isn't it? That's exponential growth. So functions that can capture exponential growth can be very, very useful in such situation. Okay? So the waning of a thing I've talked about, IRS, for instance, the indoor residual spray, which, for instance, can be measured using this Gaussian function you see here is an exponential decay function. Because once you see inside the exponential minus anything, it can bring about its decay, right? But this one now, we call it Gaussian function because you know that originally a Gaussian function should behave like a bell, have a bell shape, isn't it? But we can also have half Gaussian. Are we together? Where we take it from the, and for a Gaussian function, that's just a normal distribution, isn't it? The mean there, mean is the peak. Are we together? So where the function may not be able to take values below the mean, for instance, we are talking about IRS. When it is deployed, it has the maximum efficacy, right? The efficacy is maximum at that point when it is deployed, and over time it begins to do what? Begins to wane. So I may not need the other part of the bell shape. I just need the part of the bell shape that starts from the peak and does what? And wins. Do we understand? So that kind of function can help us. So we just truncate it. So we do half Gaussian. We don't do the full Gaussian that can go both to the left and to the right. And there are situations where we take the full Gaussian too, depending on the situation, what we are modeling. So all these things that we are talking about, they are components of models that we can use to capture different components or different aspects of the process, because we are talking about process-based models. Process-based models. And the question we are trying to answer, which determines the way our model will come and the things we factor into our model. For instance, now I'm trying to check effects of IRS on malaria transmission dynamics in Kebbi State. I've mentioned IRS. It means that in formulating my model, I must necessarily bring in what? IRS. Is that okay? And that is the beauty of a mechanistic model. You can use mechanistic model to check different scenarios. That may be the limitation of the empirical models, for instance. In the empirical models, what is not in the data cannot be assessed. Is that okay? For instance, we have not brought in vaccine before, but we want to see if we bring in vaccine, how can vaccine help us reduce the cases we are having? If we bring in these amounts of vaccine, to what extent can the cases be reduced? You can do that. It's like you are doing virtual clinical trial. Is that okay? You are doing virtual clinical trial. You can use mechanistic for that. It has that strength. You may not be able to use empirical models for that kind of thing, because if, for instance, where vaccine has never been present in the data, you can't assess what is not present in the data using empirical models because it was never there. And then scenarios, for instance, Prof was talking about counterfactual scenarios. Those are things that didn't happen. And you are trying to check if it had happened. For instance, you want to do impact assessment and you want to see how well as our maybe vaccine worked. So you consider a situation where if there was no vaccine, right? What would have been the situation? But now that we have the vaccine, and compare and take that difference gives us the impact of vaccine, right? So that's a good one for mechanistic at that, which can also give you a leverage over some other ones. Okay, so we go on to other important function. Logistic growths. Yes, we're talking about logistic equations the other time, right? But there's also logistic growth model. And what, like you have that logic function that looks like S Do you notice it's like S? Eh? So it starts and then start growing and then gets to a point at plateaus. Is that not? Good. So in population models, logistic growth models factor in what we call carrying what? Capacity. That means the population cannot grow beyond a certain level. Is that okay? Cannot grow. And when you solve this model, you're actually going to be having regression. The equation, the solution in form of a logistic. Is that so? But this is actually the where it stems from. Where we have that our K is what we call the carrying capacity that limits the growth. So, okay, so Prof is asking why? Why? So I'm throwing that question. So why? Why are we putting carrying capacity? Why are we putting carrying capacity? For instance, let's say this is human population now. Can we do this for human population? Okay, you are talking, right? Do you want to give me an answer? Tell us why the need for carrying capacity, and where can we really use this kind of situation, this kind of thing?
Okay, I think carry capacity is used to the population growing out of band, and I think is used in a population-based model. Oh, okay, sir. A very good example would be in terms of aquaculture, where we're trying to grow fish, and then so to reduce the reproduction, the growth of. Okay, so to control the growth and the reproduction of more fishes, it can be used in that.
Trying to control the growth is that we are trying to represent the reality. Okay, if you have okay, somebody wants to say something here.
I want to believe that we can describe carrying capacity that describing with this hall. Now, this hall is enclosed. Now, if we let people in one by one, there is an extent to which people can be let into this hall. So that is just a layman's definition. So, and in mathematics, we say it is bounded. The whole place is enclosed, it is bounded below and above. So if we want to remove the upper bound, remove this extension, then we extend it maybe to very far infinity. Anybody can just come in, and so that's just a layman's illustration.
Thank you so much. Okay, so that's a very good one. So, okay, Prof wants to say something.
Carrying capacity for human population. The reason why is that, like now, you have a fish pond, right? Where you are keeping tilapia. You know that after a few months, they will be growing inside, right? And then they will produce themselves. They will produce. Once they produce and you don't create another space, what will happen? They will be eating themselves. Are you getting what I'm saying now? So, but for human being, you cannot do that. So, no, you cannot even use it for human being. You can't use it for human population. Do you understand what I'm saying now? Because human population does not grow the way fish grow. Do you understand me now? Like fishes now, you can put them in a pond. Now, so the carrying capacity has to do with the resources, the space, everything you have put together, the water, the feeds, and all that, come together to play around that. So once the number of fishes that you put is growing above the limit of that pond, you have to remove them to another place, or else there will be killings. They will be killing themselves. There will be, predators.
Thank you so much, sir, and thank you, Mas, for that contribution. So necessarily, if you want to increase the space and the resources, if you want the fish to keep having space to grow, what should happen? What should you do? You increase that K, isn't it? The capacity, you increase it. So the more that case increase, so then we have everything. So you can't go beyond that. So that's why, like I said, it's going to actually give you an S shape if you plot this kind of function. If you can see the solution now. Do you see the solution? You're having as what? K over 1 plus what? You can always express your regression model like this. You know that. Your regression model can always be expressed like this. So that's why you see that it follows that S. And this is the foundation of it, the mathematical foundation of it. All right, thank you so much. You see, this is the plot. So that K, so we have chosen K to be 500. Do you see it does not go beyond 500? Eh? What happens? That population cannot go beyond 500, no matter what. Okay, thank you. Of course, we talk about basic calculus. I'm trying to check my time, and then let me stop at this point because I would like to entertain questions and people can also go and eat. So questions, let's get to interact and ask questions. Okay. How many of us are having questions so that we not overshoot our time again? I have how many hands up? 2 hands up. Good. 1, 2. So you can come forward, sirs.
Thank you so much for this nice presentation. It was really helpful. I want to ask a question with respect to something that I've been engaging with so far and I've not gotten an answer. Because everybody keep telling us that we've taken it to be a constant. That is with respect to transmission rate.
Okay.
In many publications, classes like this, people just tell you that in reality it's not like that, but we've taken it to be. Why do we always take transmission rate to be term invariant?
Okay.
Because in reality, like that does not appeal to what is happening in reality.
Okay, thank you so much. Yeah, we can, can pass to the other person. Thank you so much. Now, I would like to say that I mentioned the other time that in models, there are assumptions. Is that okay? Some assumptions are simplifying assumptions. For instance, you are going to do some analysis and you don't want the analysis to be too complex. So you just make those simplifying assumptions to make your analysis easier for you. But like we said, okay, so you said most of the papers just use it like that, but there are papers that also don't use it like that, right? Because there are also theories if you have time-dependent functions which is called non-autonomous systems. There are also theorized such models. Even if you are interested in going data, right? But going data, you don't bother your head because that's just fitting straight into your code, and then you run it. The time varying something produces whatever you want. Is that okay? And we have papers actually where we have used time varying transmission rates, and then we have produced a result out of it. So if you are interested in the result that focuses on theoretical analysis of the mathematical people, then you begin to talk of those the theories that has to do with non-autonomous system in terms of Floquet theory and the rest of those things. So you can talk about them. However, if you are just interested in going data, you don't even need to bother yourself, like I said earlier. So you just factor that thing as time varying, which we have done. We have papers in that, and it just gives you. But the basic thing is that people make simplifying assumptions just to make their own work analysis easy for themselves. That's what they do, not because that is the reality. But the question you may want to say that is that not going to towards reality also? Also, most of the time when we are doing mathematical analysis, You are just looking at the long-term behavior. Is that okay? So you are analyzing around the equilibrium. You are analyzing around the equilibrium. So whatever you see with that constant, if you say that something, maybe the disease decreases as maybe certain intervention increases, that direction cannot change even if you put time varying function. Is that okay? It's just the value and then how it varies over time. The variation, the variation in time will not be there. Do you understand? But the direction of your finding will still not change. So that's what people do when they bring in such simplifying assumptions. Okay, but you still say you have questions. Please, can you still give him the mic?
Yes, with respect to that, I want to believe that the transmission rate is like a product of two things.
Yeah,
You're talking about the average number of contact rates
yeah,
and the probability of this contact resulting in transmission.
yes.
So are we saying that these two things are insignificant in our model result? In our model result, that is why we always take the transmission rate to be constant.
Okay, so I'll give you an example for malaria now. In malaria, contact in malaria means biting, right? It's biting, mosquito biting is what contact means. And then probability of transmission. I just mentioned the other time now that we can model that biting rate as a function of time. And I showed you an example. And there are other ways also, other ways we can even bring in time variation into it. Do you understand? So we are not saying, so we know that transmission rate is a function of contact and probability of transmission. We know that. And we mentioned that that can vary with time. And so that's why, depending on what we are modeling, I just give you an example of malaria. We also, all of us gave examples too. We talked about Lassa fever. We talked about what again? Cholera, where we can bring in time varying transmission rates. So it's you who is modeling. You have control of all of these things. So you are the one who decide how realistic you want your model to be. So if somebody sees your model and says that you are using something constant where time variation would be of importance, then can challenge you, and then, or you do the right thing and say you are bridging the gap in the literature for what used to be done that does not really represent reality. So you can do that. You are in control of it. Yeah, thank you.
Now, if you look at the data in reality, is the transmission rate, right? If you remove that beta is apart from the contact rate and the probability of which is embedded in the beta, is a function of the social factors. Because for you to have contact with people, there are social factors there, then the ecology. So when you talk about beta, actually, it's a very complex.
Yeah.
The real
beta.
In fact, most times we are supposed to use some probability distribution to capture beta. Do you understand? It's probabilistic. Do you get me now? It's not deterministic. But the reason why, in trying to, as a mathematician, you want to find a way, you are going somewhere, you hit a rock. It's like water. You always find a way out. So in trying to simplify, people go and say, okay, let me assume that my beta is this. But in reality, beta is not exponential. We use exponential. It's exponential distribution. We assume that beta is exponential, but it's not exponential in real time. So, but, there are trade-offs in modeling. What people are interested in. Are you interested in transparency? When you are transparent, you want to just understand what is going on in a system. But if it's a model has to be realistic. When you want that, you need to put in a lot of things. And challenge is also the fact that data. You don't have enough data to put whatsoever you want to do. So there's a lot of people to make assumptions around there. In fact, I used to discourage my students that if I'm not sure anybody is estimating beta. Do you know why? The data we have is cases, but beta is transmission. So what produces the cases are what? The transmission.
Yeah.
So you cannot use cases to estimate transmission.
Yeah.
Do you understand me now? So it's not something. So these are things that people play around with, but it's high probabilistic. You understand? So I think these are things we have to.
Thank you so much, Prof, for that input.
Thank
Okay,
you, sir.
so the question, yeah.
Sir, I want to ask, how do we have access to this slide?
Okay, no problem. We'll talk about that. And another thing again is that most of the time, you see, everything taught between now and yesterday, you can see them on our YouTube, right? Everything is uploaded immediately. Channel where you can see everything. Like Prof said this morning, Dr. Yes, Dr. Lasmin said, sometimes we want to ask for materials, but we don't read them. We don't really read them. We are just getting them. So it would be good to go to that platform if you want to learn and sit down and learn real time. Yes. So just look for that channel and read and get stuffs. But if you now need something to practice, all those hands-on session will give you something to practice with. Is that okay? But if it's what to read, most of the time, I know we don't. So, but what we encourage you is that we want you to get really busy with the work by visiting that platform and then listen to the talks that have been given before and take your own jottings. It's good like that. Than to just collect materials that we don't use, except for the hands-on, which we will give you. Thank you. All right. I want to believe the questions are taken, and thank you so much. Okay, online. Okay, sorry. They said there's online question. Okay, can we have it?
So the question is from Charlotte Aima.
Okay.
So she's asking on the function of time.
Okay.
You talked about seasonal and peak transmissions for malaria.
Okay.
Can this model be deployed to capture timing for seasonal malaria chemoprevention as well for children?
Okay, yeah, thank you. For seasonal malaria chemoprevention, which you know that it for instance in Nigeria, how many rounds do we take in Nigeria? I think 3 or 4. Mr. Shim, how many rounds? 4, 5. Okay. And that is always towards the high transmission seasons. Like WHO says that you don't deploy seasonal malaria chemoprevention to states that have rainfall year round. So you want to consider such states that have high transmission season that's very short, between 3 to 4 months, thereabouts, within a short time, not that you're having high transmission setting for 8 months, 9 months, because people are to be taking medication during that you take medications. And because, like we call it seasonal malaria chemoprevention, so we can actually use our seasonal function, right, to capture that. And in fact, we can use what is called piecewise continuous functions, because in that situation, if each of the rounds can be captured by piecewise, continuous functions, for that matter. So I yes, but this one is, if you look at this one, you realize that this seasonality is a function, this seasonal function, which just is continuous like that in time. So that's not the way chemoprevention behaves. If I want to think chemoprevention, I just talked about piecewise continuous function because of the way it is taken. So what you want to model determines the function you will use. You don't just say, oh, let me use any function. No, you think of what do I want to model? What's the process? How does the process behave? I needed to know what is seasonal chemoprevention for me to model it. And that's why Prof was talking in the morning that I must know the system very well. So if you don't know it, you can use a wrong function to model something. So depending on the system, what component, the process you are modeling, it determines the function that you use. So I wouldn't want to use a continuous seasonal function like this for chemoprevention. Yeah, thank you. All right. Are we done with the online participants? Thank you so much, everyone, and enjoy the rest of your day.
Let's appreciate our facilitator. Let's clap for him. All right, so before we go for our lunch, let's listen to the following announcements. Yeah, so those who have not registered their names, please go to the protocol units, go and register your name. So we want to confirm if you are here. So we want to know the number of those people that actually attend this workshop. So please go and register your name. It's very, very important. Then after lunch, please don't let us rush back to our various hostels. Let's come back here. We'll be doing our grouping. So we'll be grouping us to different projects. So if you are not around, you will not be part of any group, which shows that you will not be part of any project. So please let's come back here after our lunch. Then I would like to announce that our participants, we would like them to take their meal first before Ikamda people follow thereafter.